All right, PCH, this week we've already talked about logs and how we can use them to solve exponential functions. We've already talked about log properties, and so now we're officially ready to start solving log equations. And so this video is going to be pretty short, and we'll get started with some pretty basic warm-up problems. And so if we're looking at number 1, we see that we have log base 14 of negative 3x minus 1 equals log base 14 of 3x plus 5. And what we're looking at here is if we have a log base 14 of an argument equal to log base 14 of an argument, those arguments are going to be equal to each other. If you think about it, this is really similar to that situation we found with exponential functions when we had, let's say, 2 to the 3x plus 1 equals 2 to the third, we'll say. If we have a base to the stuff equals the same base to the stuff, those stuffs have to be equal to each other. The same thing applies with logs. If we have a log base 14 of an argument equals log of the same base, in this case 14 of an argument, those arguments are going to be equal to each other. And so, of course, we can set those equal to each other and solve for x. I'll move my negative 3x to the right side, my negative 5 to the left, so we get negative 6 is equal to a positive 6x, and we get x is equal to negative 1. Awesome. Ladies and gentlemen, we just solved our first log equation. All right, number 2, we have log base 6 of 3x equals log base 6 of x plus 8. Again, we see that we have a log equaling a log, and both those logs have the same base, and so we are able to set those arguments equal to each other. All right, let me know what you get. I really hope when I look at this ed puzzle before we have this class on Monday that all of us were able to get to x equals 4 for the second problem when we set our arguments equal to each other. All right, now we've done some warm-up problems, let's move on to a few more difficult problems. And so for number 1, check it out. We have a log that's isolated equal to a number. When we have a log like this that's in standard form and we have our variable and our argument, we're going to solve this by rewriting this log as an exponential function. And so remember, when we were trying to solve an exponential function with a variable in our exponent, we'd rewrite it as a log. But if we have a log in our variables in our argument, we're going to rewrite it as an exponential function. And so again, if the chubby hand helps you, 4 to the third is equal to 2x plus 1. Let's write it down. And we see that now our variable is no longer in our argument. It's set up in an equation that we can solve for. And so that's what I'm going to have you guys do right now. And you'll see in that really ugly looking bubble down there in the bottom right corner of the screen that I ended up getting an x value of 31.5. All right, let's move on to another problem. So now, again, unlike the first problem we just did of this extra special practice, our log is not isolated. It's not in a standard form where we can convert this to an exponential function and solve for x yet. And so our first steps are going to be, again, to isolate this log. And so first, I'll move that 2 over. Then I'll divide by 3. I know you guys can all do this math on your own. I don't want you to sit here and watch me do it, so I'm going to have you finish the problem for me. All right, I never promised it'd look pretty, but there she is. X is about 3.828. And so I'm curious, after doing 2 problems, if you had to say, okay, these are the key steps that we follow when we're trying to solve logarithmic equations, this is what they'd be. Go ahead and share. Yeah, so I've obviously talked a ton about how much I love logs and how much exponential functions and logs are just so cool when you put them together. And so hopefully you came up with some key steps along the lines of, okay, my first order of business is to isolate my log. So I have log base something of my argument is equal to a number. Once I have my log isolated, then I can rewrite it as an exponential function and solve for x. I think that's so cool because when we were talking about solving exponential functions, the way we did that was by using logs. And now to solve logarithmic functions, we need to use exponential functions. Math is just the best. That's all I can say. All right, last problem before we move on to doing some on our own. Okay, number 3. As we notice on this problem, just like in our warm-up, we have two logs and they have the same basis. So we must be able to set their arguments equal to each other, and that's how we're going to solve for x. Unfortunately, that's not going to work out for us on this problem. The main reason being this guy over here. Having some number outside of our logs messes that whole thing up for us. And so we cannot set these arguments equal to each other because we know that both sides of these equations are not going to be just a log base 10 of something equals log base 10 of something. And so we have to figure out another way to somehow get that x variable out of our arguments that we can solve for it. I'm curious if you guys have any ideas. Hopefully you looked at this and you're like, hey, wait a second, we just talked about log properties, and we know that if we have a log base something of an argument plus a log of the same base of an argument, we can make those one log with their arguments being multiplied together. And so I'm going to go ahead and rewrite it like that. Log base 10 of our arguments being multiplied together. X times x minus 3 is equal to 1. And now what we see is, hey, yes, finally, like we talked about, we have our log isolated. It's in like its standard form, if you want to refer to it as that. And so I can rewrite this as an exponential function and solve for x in that way. You guys go ahead and finish the problem for me here. After doing some factoring there, I get x values of 5 and negative 2. Now I'm curious, whenever we were solving exponential functions, we decided that, hey, we do not have to plug in whatever values we get for x back into our exponential function to see if they work. Because we know that we could have positive exponents, negative exponents. It didn't matter. Like, that's still going to allow us to solve that function. It's not going to create any issues for us. I'm curious, do you think that same thought process applies for logs? No, it doesn't. Remember, way back in that lesson when we were talking about graphing logarithmic functions, we said that our base of our log has to be greater than 0, and it cannot be equal to 1. If we have a positive base we'll say 2 in this case, whether it's to a positive exponent, whether it's to a negative exponent, both of those answers, which is what would equal our argument, are going to be positive numbers, right? It doesn't matter what positive number we have for our base. Again, it doesn't matter what exponent we have. Our argument is always going to be positive. And so that's something we have to check for. There is a potential that an x value that we solved for, when you plug it back in, gives us a negative argument, which means that that is an extraneous solution. That does not work for us. We do not include it in our values of x. And so let's go ahead and plug these solutions in to check. When we plug 5 in, we get a positive argument here. of 5, as well as a positive argument of 2 for this second log here. So it looks like 5 checks out. When we plug in -2 already for this first log, we get an argument of -2. That's not going to work for us. And so we can already say, hey, -2 is an extraneous solution. That's not going to work for us. And so the values of x that satisfy this function is 5. All right, as we get prepared for class tomorrow, I want you guys to work through these 3 problems as a check for understanding. Submit your answers on the Edpuzzle, and then we will talk about them in class tomorrow. All right, see you guys then.